Hi guys, we'll just get started in a minute or two. I just want to give a couple of minutes for everyone to join.
Hi, everyone, and thanks for joining us today. The Lovelytics team will be presenting on predictive analytics and Alteryx. And just so you know, the meeting is being recorded, so we will have it available on our YouTube channel afterwards, and we will be sure to send out the link so that everyone can go back and review. And then in terms of Q&A, please feel free to ask your questions in the Q&A bar, as well as use the chat feature if you want to send it directly to me. We'll try to pause at certain points in the demonstration where it makes sense to allow for questions, but we'll definitely be leaving time at the end as well. So with that, I will put myself on mute, and Amar, I'll let you kick it off.
Thank you, Mike. Given the content that we have, I'm not sure if we can cover leave space in between, but we definitely have 10 minutes in the end for questions. With that said, hello, a very good afternoon, everyone. Thank you for joining us on this webinar. We are super excited to have you. And in today's webinar, we'll talk a little bit about our data science approach and show it to you in action. So let's get started. This webinar is brought to you by Lovelytics. We are a data consulting firm and we specialize in everything data. Our tools of innovation primarily consist of Alteryx, Tableau, Snowflake, and Salesforce. We are also an associate partner with Alteryx, and our primary goal is to ensure that our clients get the most out of their investment in Alteryx. In case you're interested, you can reach out to us on these platforms. Please feel free to connect with us. We'll be thrilled to be a part of your data journey. I am Amarendra. I lead our Alteryx practices here at Lovelytics. I am responsible for the enablement and adoption of Alteryx with our clients. I happen to recently move to Toronto, Canada from the US. I've been using Alteryx for about 4 years now, and I'm one of the leaders. I was one of the leaders for the Philadelphia Alteryx user group back in the US. I'm currently working on my partner certifications and was recently nominated as an Alteryx innovator and advocate. So before we move on to today's agenda, I'd like to pass on something valuable. I've curated a list of resources that can help you get started or get better with Alteryx. To begin with, we have the Alteryx community, a one-stop shop for everything Alteryx. You will find use cases, discussions, tool mastery series, where they teach you how to use a single tool in detail. We also have custom macros and a whole lot more, so be sure to check it out. Next, we have the Alteryx Academy, a learning playground with interactive lessons, weekly challenges, and certifications. Alteryx also has a podcast where they discuss anything from new features, user groups, data science trends, enablement, so on and so forth. Finally, a quick conference update. Alteryx conference, formerly called Inspire, is now rebranded as Analyticon. And due to the pandemic, the postponed date is now June 2021. For registrations or refunds, please use the URL that you see on the screen. I'll pause here for a quick second. You could also email analyticon@alteryx.com. So for all the data people on the call, Alteryx has these cheat sheets for both Python and R. These are URLs, and we'll be sending them out to you once we are done with the webinar. These documents can help you with replicating the most frequently used functions from Python and R in Alteryx. All right, so let's dive in. So our definition of predictive analytics is to use unbiased and reliable data to produce predictive models with dependable outcomes. Here at Lovelytics, we use a simple 5-step process that keeps us grounded and lets us see the big picture. So the step 1, we start with data quality. So when was the last time you bought something expensive and realized the quality was not up to the mark? Does this sound relatable? The same applies here. We need to make sure the data is clean, complete, and sensible. For example, filling in all the null values, removing outliers, and etc. The software engineering concept garbage in and garbage out applies to machine learning as well. A poor quality data model will result in a poor quality predictive model. And step 2, we move on to data exploration. Here, we take a look at the data and visualize it to understand and decode the underlying patterns and relationships. This helps us to think about what predictor variables we should use in the model. For example, if I'm predicting how much a person will earn in the future, I want to know his or her education level, which industry that they belong to, etc. Relevant variables are key and are most useful for our models. We then move on to feature engineering. This is nothing but a data modeling technique, and it is quite specific to machine learning. Here, we try to enrich the data set by using existing variables to create new ones. For example, we can include variables like how many people are within each group. And we can also find out from a given text data, we can, at a granular level, we can just aggregate all of that and come up with a new field which we are then shown the aggregated level of data. And this feature engineering process is really useful and helps the model understand the critical relationships in the data. And step 4, we have model building and training. This is an obvious data science step where we leverage several machine learning models to see which one performs the best. And it usually comes down to your specific problem and how much data that you have on hand. Once our model is ready, we move on to the final step, that is the validation. This, according to us at least, is very important and is often overlooked. Validation speaks for the predictive capabilities of our model. Great performance is usually key for any predictive model. Here, we don't just analyze the accuracy, but we also use other metrics to evaluate and understand how well the model performed and how we can further improve it. An over-engineered model becomes quite apparent in this step, and that's the reason it's very important to validate all our models. So now that we have this 5-step process, we take this process and standardize it across all the tools that we use. To show you how we do it in Alteryx, I would like to introduce you to Sean Koo, who is one of our lead data scientists on the team. Sean, take it away.
All right, thanks, Amar. So I'm going to share my screen, and then we can get started. All right, so thanks everyone for coming for today's session, and good afternoon to everyone. So my name is Sean, and I'm currently the lead data scientist at Lovelytics. So what I do is I code a lot in Python and R, and then I also run data science workflows on Alteryx. I do a little bit of Tableau depending on the client requests, and I'm also really familiar with Snowflake because that's an integral part of the data pipeline that we often help clients build here at our company. I've also been certified in the designer core as well as the partnership certification. I also have the certified associate Tableau certification, although I don't use that too much nowadays. So my background is mostly in data science, and for me, it's been really exciting to use Alteryx because it helps me to abstract away all the code and all the considerations of having to write a really lengthy piece of code, and help me just focus on the data science bits of building the workflow. So I'm going to give a really quick introduction to kind of build on what Amar talked and give you a quick introduction to various tools on Alteryx that help us to achieve the goal of predictive analytics. So the first step that Amar talked about was the data integrity and quality check. And over here, we can see that there are quite a few tools that we can use on Alteryx that will really help us in this respect. So for example, I can use the browse tool, and the browse tool is actually really useful in telling me if I have any missing data or some data that could potentially be problematic. This is something I'm going to show you later in the demo as well. And some of the other simple tools we have are like the data cleansing tool, the select tool that help me to make sure that things are in the right data type. And we also have the unique tool to make sure that I remove any duplicates beforehand. And the last tool, the imputation tool, if I have any missing data, sometimes I want to impute it with the mean or the median of that variable, rather than just imputing it with 0, for example. And that's where the imputation tool comes in really handy. So that's for the first step. And already in the first step, we can see there are so many tools that are available on Alteryx for me to work on checking the data and making sure that the data is in the right place before we move further down the predictive analytics workflow. The second step is the exploratory data analysis. And here, we're trying to understand our data a little bit better so we can identify more accurately what variables would be important for our predictive model. So here, we have another range of tools. We could easily do a simple summary and aggregation of the data, or running total, for example. But for some of you who are a bit more visually minded, we are also able to run custom plots on Alteryx itself. We don't even have to step outside into another coding software like R or Python in order to run these plots. So for example, here we have my favorite, the histogram, the violin plot, the scatter plot, association rules, and heat map as well. So all of these things are really useful in understanding relationships and patterns within the data itself. And I'm going to show that to you in the demo later. And again, a picture speaks 1,000 words. Sometimes just having a simple chart helps you to understand the data a lot better than looking at a bunch of tables. So that's the second step for exploratory data analysis. The third step is where we try and build more features into the model, where we try to engineer, squeeze out more usefulness out of the variables that we have currently in the data. Again, many tools for this. We can use the text columns or the regular expressions tool to kind of squeeze out a bit more data out of our existing unstructured text or structured text data, basically. We also have the range of formula tools that will help us to create new columns that better encapsulate the relationship between the variables that we have, the data that we have, with the variable that we're trying to predict. And of course, we also have the join tool as well as the weighted average tool that will be really useful for us if we want to aggregate certain variables and join them back to the data set. So that's for feature engineering, and again, a really important step. But the next step is actually the one that most people are interested in, and that's the model training step. And of course, this is the most fun step because that's where you're actually running the predictive models itself. So here, you can see that you have the widest range of models available, from everything from naive Bayes, which you kind of learn in class and you drop in the next class. But you also have things like linear regression, logistic regression, which can perform very well under many circumstances. But you also have all these new models, such as the random forest model, the boosted model, and even a neural network. And the best part about this is that you don't have to run any code to run any of these models. Even for me, as a data scientist, when I type in Python, sometimes it gets a bit annoying. You wish you had something simpler to work with. Alteryx is really that answer for you. So that's for the model training stage, and it's amazing because these are just 8 out of these are just 8 models out of all the models that you have access to. So I couldn't put all of them into one page, and that's we'll take a look later. What the other options are. The last step is validation, and I think Amar rightly said that validation is basically the most important step because for us it's really important that we check that the model is performing exactly the way we want it to. or to the best of its abilities. So here we have the really helpful tools like the cross-validation tool that helps you make better use of your training set, the scores tool that helps you to make predictions, and we also have model comparison tools that help you to understand the difference between the models and how they're performing. So all of these tools are available on Alteryx itself. And the best part about this is that you don't need to know any R or Python to run any of these tools. And they perform the exact same functions as they would on the programming languages. And to me, as someone who's comfortable coding and someone who's also comfortable on Alteryx, it really makes things a lot easier when you look at icons instead of having to read through someone else's code, just because you're really focusing on what exactly is going on in the workflow, and when you can see what's going on when they're all linked together as a coherent workflow, as opposed to reading through lines of code. So that's, for me, as someone coming from a coding background, this is a really huge plus. So now that I've gone through all the different tools on Alteryx and how they kind of relate to the 5 steps that Amar was just talking about, now we move on to, hopefully the most exciting part of today's webinar, which is actually looking through the use cases and the workflows themselves. So the first use case, the one that we talked about, was a marketing campaign. So we got data from a direct marketing campaign that was conducted by a Portuguese banking institution sometime between 2008 and 2010. So this was done over telephone, which obviously is kind of outdated by today's standards. But a lot of the data that we've uncovered is equally applicable to modern marketing channels, especially if we're thinking about, marketing on Facebook, marketing on Google. All of these things are still pretty important. And in this data, what we have is anonymized demographic data. We have the age, we have the occupation, the education of the individual. We have their current status with the bank. So whether they have taken up a loan, other loans with the bank, whether and how much money they have in their bank balance. And we also have the interactions from previous marketing campaigns. So the objective here is we want to predict which customers ultimately subscribed for the bank's term deposit product, which they were trying to advertise through this marketing campaign. So for those of you who know a bit more about predictive analytics, this is what we call a classification problem, where you pick yes or no, so that the model tries to tell you, did this person sign up for this product? And this is really useful in many cases because sometimes you want to be a bit more targeted in your approach. You want to be able to identify which customers are most likely to subscribe for your product and preemptively reach out to them or spend more resources on converting them. And that ultimately improves your conversion rates and reduces the cost per conversion. And these are all important things in the world of marketing. So this is how the workflow looks like. I'm just giving you a brief kind of like high level view of the workflow before we actually dive into it. But if you look here, we have 4 boxes and they kind of map very cleanly to the steps that we talked about earlier. So here I skipped the feature engineering step just because I don't have that much time to go through every single step. But you can see that for us, it's pretty consistent where we have these 5 steps that exactly match to the workflow that we have. So what I'm going to show you now is I'm going to go through the workflow itself. And you will see how easy it is to move from the start with a CSV file all the way to the end where you have a trained and working model. So right at the start over here, so I'm just going to zoom in a little bit more. There we go. So the first step we have is obviously importing the data itself. And over here, you can see that we can pull in a CSV file. Here, my CSV file is a little bit special, so I had to put a different delimiter. But the most amazing thing is when I click on the browse tool, so I'm connecting this to the browse tool, and it automatically shows me a summary of, it shows me the first couple of rows of my data. But more importantly, it looks at I can actually see my data quality immediately when I look at the color below, below my, the column name. And immediately at a glance, I can see that all my data is perfectly fine. There's no missing values. There are no string characters with, white space in front or at the end of it. And this is actually one of the most useful things about Alteryx, because on Python, I would have to literally check each column manually. And there's something simple like this is not as easily available on Python. So this simple visual check helps us to know that, okay, we've imported the data, everything is good. We can go straight ahead to looking at the data through exploratory data analysis. So obviously I put a little tool here, standard data cleansing. This is the paranoid person in me saying that, hey, we should just put it. I usually do this, just because a lot of the data that we work with isn't as pretty as this, and so that's why that's always there. So over here, you see that I have a couple of hypotheses of things that I want to check for doing this exploratory data analysis stage, and that's kind of like the pretty standard thing I do. So whenever you give me a predictive problem, my first thought is, okay, let's check a couple of things that we think might be really related to the outcome that we're trying to predict. So the first thing I want to look at is not, before even we talk about things that might be related to what we want to predict, is to think about whether or not there is an imbalanced data set. What do we mean by this? So sometimes you might have more people who rejected the product than people who actually signed up for the product. And this tends to happen, right, for any marketing campaign. In fact, for most marketing campaigns, if you get a return of like 10 to 20%, that's considered already pretty good, especially if you're talking about online marketing. So in this case, what we want to look at is we want to check for class imbalance. If there are more people who declined to sign up for the product than the people who actually did sign up for the product. And the reason why this is worrying is because when you're trying to train the model to classify it correctly, they need to have a good understanding of how many of each class or how many of each outcome there are before they can predict it more accurately. So over here we use the summarize tool to aggregate the counts by the response variable, and we can see here immediately that our suspicions were right. We have nearly 40,000 people who did not sign up for the product, but we had about 5,000 people who did. So we have about one in every 10 people signed up for the product, essentially. 1 in every 9 people, sorry, my math just failed. But that's kind of worrying, because that means that for every one person, 8 persons rejected the product. And therefore, there is a class imbalance here, and we have to deal with it later on. So now, having established that, I'm going to look at the 3 hypotheses here that I have written out. So the first hypothesis that I have is, hey, if my customers talk longer to the salesperson, then they're probably more likely to sign up, right? Because they're talking longer to the salesperson, they're interested, they're finding out more details, so they are more likely to sign up. So what I use here is a Violin plot, which allows us to look at the comparative distributions of that variable across different categorical variables. So here, I'm grouping it by the outcome variable, which is whether or not they signed up for the product. And you can see here the duration of the call. You see that the average duration for people who did sign up is higher than for people who didn't sign up. And that kind of fulfills our hypothesis. More importantly, because we're looking at a distribution and not just the average, we can see that this distribution actually continues it's kind of skewed towards a higher duration. So it's not just the mean, but it's also a significant amount of people who did sign up who actually do talk longer to the salesperson. We can also see something really interesting on the no end. We have a very long tail. For those who are more statistically minded, we have a really long tail over here, where there's some people who spoke up to almost 5,000 minutes, which is incredible in total. So sorry, 5,000 seconds, I believe. Sorry. So here, these are the people who probably talked for really, really long, and in the end decided it's not for them. And so this, just by looking at one plot, we're able to understand data in so many different ways that we weren't able to previously just by staring at the tables. So that's one of the most amazing things about being able to visualize the data so easily on Alteryx itself. So the second hypothesis is, hey, for those with higher bank balance, the richer people, maybe they're not as likely to talk so long, because for them, it's a relatively simple choice of whether or not to sign up for the product. They have a lot of money sitting in the bank, so they might be more open to the idea. So we ran a scatter plot on this, and the scatter plot seems to suggest that that is the case. If you look at the, it looks like a nice triangle over here. And what that suggests is that for a lot of people with a really, really low balance, or basically close to zero, they looked like they spent a lot longer talking to the salesperson. And for the people who had a higher bank balance, on average, they spent less time talking to the salesperson. So again, hypothesis 2 seems to be about right. And we've got 2 out of 2, which is a really good score. So hypothesis 3 then is whether or not the marketing campaign was successful in targeting workers in the, the age range of 30 to 50 years old. Basically people who are starting to have quite a number of money in their savings and are probably thinking about some kind of financial instruments to preserve, the value of that money a little bit more. So here, my favorite chart, the histogram. And we can see immediately from the histogram, from 30 to 50, that represents a huge chunk of people. That's clearly more than half of the people that they were talking to. And you can also see that after 60, there's a huge drop off as well. So that suggests that there was a deliberate attempt to actually keep it between maybe 25 to 60 as opposed to 30 to 50. And that would kind of suggest, suggest that this targeting or hypothesis 3 is kind of there, but we should probably amend it to like 25 to 60 for the age range that we're talking about. And so I hope that gives you kind of a good idea of how you can use Alteryx to quickly understand your data. And we're not just talking about running numbers, we're talking about looking at charts. It can really help you understand what's going on in your data. So the next step after this, after the exploratory data analysis, is for us to run the machine learning model itself. So we're skipping that third step of feature generation and moving to the model training process. So if you look over here, what we do, and these three tools I'm actually using as part of a custom approach to implement stratified sampling within Alteryx itself. So that's unfortunately not available out of the box, but this is something that you can easily do by yourself, and this is exactly how I've chosen to do it. You can see that there's something strange going on over here, because you would expect some kind of line going through here. You can see that from this little small icon here that we actually have a wireless connection. And so this is one of the nice things that Alteryx has that allows you to really keep your workflow neat and tidy. And again, so easy to understand for anyone who's just looking at this for the first time. So because of the class imbalance, we do stratified sampling so that we can train the model accurately. So stratified sampling just means that we ensure that the training set, what the model is learning, what data the model is learning from, and the test set which we use to evaluate the model have equal proportions of yeses and nos. And that's our way of ensuring that the model is actually getting the right, getting a good an accurate representation of reality every single time it's looking at data. So over here, we run 3 different machine learning models. And it's kind of the standard in the industry, which is, run a couple of models, because before we run the models itself, we don't actually know which one's going to perform the best. And that's kind of why we want to run multiple models, see which one performs the best, and then we take that one and we run with it. One of the best things about running these models on Alteryx is that we don't just run the models. And this is kind of like if I ran this on Python, for example, I would just get the model object. Over here, I can actually click and look at the report from the model itself. And I can see over here exactly which variables were statistically significant, what kind of effect did they have on the probability, because I'm running a logistic regression here. So these are all marginal probabilities. And then I can see which ones are statistically significant. And that's really important when you want to understand exactly what's going on under the hood with your data and with your model. And so I can also do this for the decision tree. And for decision tree, for those of you who know a bit more about decision trees, it actually gives me a leaf summary. So it tells me where exactly it splits. And that also is really informative, especially if I'm trying to be more accountable about how my model is actually performing. So that gives me a great idea about what exactly is going on under the hood. The last model I chose to use is the support vector machine. And it's kind of not really one of the traditional models that people use. But what I really wanted to show you with this was this classification plot. So for those of you who understand what support vector machines are, they essentially demarcate regions in a certain n-dimensional space that they will classify as yes or no. So if a point falls within that space, within that range, then it would classify as yes. If it fell outside of it, it would classify as no. And over here, what Alteryx provides you is a really nice diagram that tells you exactly for two variables where that space is. So for example, if my new data falls in this specific space, then we will classify as yes. If it fell into this space, that would be no. And that's a great way for us to understand what exactly the relationship between duration and the predicted outcomes are. And we can see over here, the model is saying, if you've talked for 1,000 seconds to almost 3,000 seconds, then we are predicting that you are most likely to have signed up for an account. And this is so intuitive and so easy to understand. And this is not something that's available out of the box for many of the programming languages. So with that done, and now that we have a good understanding of the models that we've trained, what we do next is we take the test set data and we run it through the scoring tool, which allows us to get the predictions from the trained model itself. So the analogy here is like you're taking examinations. As a kid, you have your teacher sometimes give you practice tests way ahead of the exams because they want you to do really well. From those practice tests, your teacher marks them, and your teacher tells you what the right answers are, and they explain it to you. So you learn that you learn how to answer that question a little bit better the next time. So that's what the training process is. In the testing process, the model it's as though I'm taking an examination, my final examinations. And at my final examinations, there is no teacher there to tell me if I got my question wrong. I mean, at least not immediately, and no teacher to explain to me why I got it wrong. So this testing phase is basically the best way we have to evaluate what the model is doing, and to make sure that that model, whatever predictive accuracy the model has, is likely to carry over into our future, where we give it updated data, and when we ask it to predict next month's data instead of predicting this month's data. And over here we can see that there are we use a bunch of formula and aggregation tools to calculate the accuracy of these models. So here you can see that, hey, we got 90% right with the logistic regression model. We have a 90.8% accuracy, so slightly higher with the decision tree model. And the support vector machine unfortunately falls short with 89.79%. And so this is kind of basically the most standard data science workflow that you would ever see. We moved from start to end, from grabbing data, importing it, understanding our data a little bit better, running a couple of machine learning models, and then moving on to evaluate it at the end. And you'll see that all of this is done with, I don't know, less than 30 icons, no code at all, and super, super easy for anyone, even people with no predictive analytics experience, to understand exactly what's going on without having to ask you or bug you with questions, which happens more often than you think. So this is the first workflow that we have for this presentation. And again, this is the marketing yield workflow. So now I'm going back to my slides, and we can start moving on to the second use case, which is very different from the first one, where we're going to talk a bit more about diagnosing heart disease. And you might be wondering, can a predictive model really do that? And you'll be surprised. So we took data from a 1989 study by Detrano et al., who was actually investigating whether or not a probability algorithm could help in diagnosing heart disease. So kind of ahead of his time, basically, at that stage. So the data comes from 303 patients who are undergoing angiography at the Cleveland Clinic in, obviously, Cleveland, Ohio. So the data that we have includes the age of the individual, the sex, as well as several detailed attributes relating to heart disease. So we have the cholesterol levels, their heart rate, etc. The objective here is to predict which patients were diagnosed as having heart disease. And this is, again, a classification problem. So you might think, what's the use of this when we have doctors? And there are some use cases where this is going to be really, really helpful. So for example, if you have a very, very long waiting line, you have a limited number of doctors, you would want to think about ways in which you could prioritize people who are more likely to have heart disease than not. And in most cases, some hospitals rely on some checklists to do that. But in this case, we can move beyond just a simple checklist, which will require you to take in only maybe 5 to 10 variables at most, and actually use all the data about the patient to really predict whether or not this person has a good chance of having a heart disease. And then we can prioritize that patient for further screening, and that means you have a better allocation of resources. So this is the workflow for this use case. And you might be looking at this and thinking, hey, that looks exactly the same as the workflow you just showed us a couple of minutes ago. And that's actually part and parcel of the brilliance of Alteryx, which is that these workflows that you build are actually pretty reusable, especially from a data science standpoint, when you're talking about a fairly standard process of approaching predictive analytics problems. So I'm just going to, obviously, because most of these steps are pretty similar, what I'm going to do is I'm going to focus on the differences that we have from the previous model, from the previous workflow. So if you look over here, again, if I click on the browse tool, I want to check if there are any missing data. I look over here, immediately there is no missing data. But also more importantly, I see that these are all numeric data. There's, unlike the previous use case, there is no text data or categorical data over here. So what I do is I convert the diagnosis, which is in this column, into a yes or no variable. And then I enforce the right data types just to make sure that we get the right data types, because for some of them, they're actually categorical. So for example, sex of patient, 1 actually represents male and 0 represents female. So here again, I summarize the data and I check for class imbalance. And here again, we can see that the number of no's is 164, number of yeses is 139. So this is fairly even, especially by classification standards. So we don't need to be as worried as we were in the previous workflow. And here, we look at another 3 different hypotheses, obviously, because this is a different data set, we have different hypotheses to consider. So the first hypothesis I have, which is pretty intuitive, I think, which is that patients who are older are more likely to have heart disease. And again, the Vining plot, which I think is my second favorite plot at this point. If we look over here, yes, we can see immediately that the older you are, the more likely you are to have been diagnosed with heart disease. And that obviously makes sense because we know, medically speaking, that's age is a good, as you grow older, you're more likely to get heart disease. So in this case, with the model, we are able to replicate that understanding just by looking at the data itself. We can see that there's a huge bump over here at around 60, in contrast to those who were not diagnosed as having heart disease, where this distribution is a little bit flatter, a little bit more even. And so the Vining plot, again, gives us a lot of useful information about the distribution of the data that we're talking about, especially with respect to the variable that we want to predict. And that really helps us to understand the underlying patterns of the data and improves the whole data science process for you further down the pipeline. So the second hypothesis is that patients with a higher resting blood pressure have a lower maximum heart rate achieved. Again, I'm not a doctor, so this is something that I'm just looking at for fun. And I can see that, hey, this looks like just like a random cluster of points. So this seems to me like there is no relationship between the two of them. Probably because there might be no biological relationship between the two. I have no idea. So I'm not the expert in that area. So if I look at this, what is one easy way for me to tell that there is no relationship between the 2 variables? If I look at this solid line over here, that is a line that would be produced if you ran a linear regression on this cluster of points. And you can see here that across the different resting blood pressure, if I change the value of the resting blood pressure, the value of the maximum heart rate achieved doesn't actually change that much. And that tells you that there is no relationship between the two. Because if there is some relationship between the two, then this should change a lot more in response to this variable. So hypothesis 2, we can strike that out. That's not going to work out for us. The third hypothesis is that most patients that we have in this data set have a high serum cholesterol level. And again, cholesterol levels, heart disease, very well correlated with each other. But what we want to see here is that, interestingly enough, we have a lot of people within this 200 to 300 range, and we can see that immediately through the histogram. We also have, I think, one outlier all the way out at 600, which is incredible. And actually, these kind of situations might suggest that perhaps you do have an outlier. And that's actually one of the best use cases of a histogram, which is to identify outliers where you keyed in the data incorrectly, someone forgot to put in a decimal place and stuff like that. This is a really good spot for you to identify and rectify these issues. So that's the exploratory data analysis stage. And you'll see that for the step 3 and step 4, they look exactly the same. And that's because we're running the exact same things. We are putting in the data, we're stratifying it still, just to keep it as rigorous as possible. And then we train 3 different models, and you can see that we have these models over here, and we are able to look and examine what exactly is going on under the hood for all these models. Even for the support vector machine, you can see that, wow, this is actually pretty nice, right? You can see that there is a sense to this madness. And so we move on quickly to the last step where we evaluate the machine learning model itself. And we look at the accuracy, which is just how many times they got their prediction correct. Here we have 81%, which seems low in the previous use case, but you have to consider the fact that here it's about 50-50 that we have for each of the different classes of different outcomes. So 81% is actually pretty good because they can't just get away with predicting all of one, all yeses or all nos, because if they did that, they would only be accurate 50% of the time. So 81% represents a almost 60% increase on top of that. And then we have 82%. Again, the decision tree model seems to be doing much better than the logistic regression model. And then the support vector machine, again, pretty disappointing. So that's kind of, wrapping all this up. This is kind of a pretty standard data science workflow. And I think I've shown that by basically using really similar workflows for 2 very different problems, for 2 very different industries. We are basically using the same tools to analyze all of this. All we have changed is the variables that we look at the exploratory data analysis stage. So with that in mind, so that's the second use case wrapped up. And I hope this has given you a really good idea about how you can use Alteryx as part of your data science workflows. Not just because you don't need to write code, but also because it provides you so much more insight with so much less effort compared to programming. That for me, as someone who was trained in R, moved on to Python, Alteryx still remains an excellent platform for me to run data science workflows, especially when I have to send them to colleagues who aren't as familiar with data science. This is something that they can get behind because they can easily read the comments and understand what's going on. So with that in mind, I'm going to pass the time back to Amar, who will wrap up the session.
Thank you, Sean. So what did you guys think? Wasn't that fantastic? If you couldn't tell already, we here at Lovelytics, we love Alteryx, and this tool continues to blow our minds every single day. I personally have days when I sit and gush about engineering something so sophisticated without having to define any packages or installing any libraries. So now the predictive capabilities of this tool are not limited to what we have shown you today. With 2020.2, Alteryx has released some cutting edge tools that further enable you with machine learning and text mining capabilities. PDF parsing is no longer a dream. It's just a couple of clicks in Alteryx. And also, some of the robust and dependable algorithms like Vader for NLP are now a part of Alteryx. And here is a glance of all the latest tools that are available in Alteryx. And here is where you can find them in Alteryx. If you go and scroll through the tools, we now have a machine learning tool palette and a text mining tool palette as well. And this is exactly what I've shown you on my slide. With that, thanks everyone. That is all for today. We have one more webinar in July, and here are the details. Just point your phones to the screen and a registration link will pop up. With that, we shall open up for questions.
Yeah, so maybe I can answer some of the questions that were raised in the Q&A. So I think, so one of the questions was how you would make, how would you make a case to use Alteryx for data wrangling and predictive analytics, over the big boys like AWS and Azure? So I think one of the most useful things about Alteryx is that you can actually run a lot of the, data wrangling as well as the predictive analytics tools in database itself. So those are the in-database tools that Alteryx provides. So that means that you don't even have, that saves you a lot of computational load on your computer, because you are effectively able to, move a lot of the data wrangling bits at least onto the SQL database that you have. And on top of that, for a lot of things like AWS and Azure, they're still in the preliminary stage and really getting to grips with predictive analytics. So I've used AWS SageMaker, for example, which is what they are trying to roll out as your equivalent for predictive analytics. But for that one, you actually need to know how to code in Python to use it. So again, like a lot of the benefits that Alteryx brings to you is the fact that you don't actually need to code. It's so much easier to share your workflow with other people, and I think that makes it so much more useful in an organization where you have to share these insights with other people who may or may not be on the same technical level as you are. So that would be my answer for that specific question. I think so. There was also a question about the test and train set. So the reason why that wasn't super clear in that case is because the test set, I didn't choose to use the sampling tool itself, but I can show that pretty quickly right now about how the test data was created. So let me share my screen really quickly. And so if you look over here, how the test set is being generated is what I'm doing is that I'm assigning a randomized ID, and I take a stratified 70% sample. So I take the first 70% of rows where where it's yes and where it's no, because I'm grouping by the outcome column. So after I do this, I do an anti-join. An anti-join is basically a case where I only keep the data that did not join with the other data. So in this case, on my left, I have the stratified 70% sample, which is the data I'm using to train the model, and on the right side, I have my full data set. And so because because I'm using the right part of it, I'm actually taking only the part which was unjoined, and because of that, that forms the test set. So I hope that answers the question.
So I think that was one of the questions, and I hopefully answered all the questions in the chat. This workflow is not available on the gallery. We'd be more than happy to share it with you.
So I can explain the last question I see there. So how would you explain to customers on why or how the model predicted certain things? So that's a great question. And I think that's one of the most difficult bits about predictive analytics, which is that it sometimes seems like a black box where you're giving it data and it's giving you predictions, without it really being telling you why or how it's coming to that decision. So that's exactly what I was kind of trying to show. And I know I went over this pretty quickly, but when you look at the model, they actually explain to you how they're achieving that prediction. So over here, if I look at the logistic regression model over here, the estimate over here, so for those of you who know a bit more of stats, you can probably gleam over this. But so what these estimates here actually tell you is how much of an effect and what kind of effect it has on the final prediction. So in this case, being a housemate means that you're less likely to sign up for a product, and you are much less likely to do so than someone who's a blue collar worker. And you can see that this number is smaller than this number. In contrast, if we look at a student, you actually have a positive chance of a positive coefficient here. And that means that you're more likely to be predicted by the model to sign up for the product. So those are, these are ways in which you can explain to customers how the model is predicting this, because I can actually tell you, what the model is thinking behind the scenes and the decisions and rules that it's making for every prediction that it's making. And that's kind of why, when Amar talked about how this is more reliable, it's more reliable because it's using the exact same rules and applying it to all the different cases. For those who know decision trees as well, this is telling you that, hey, if I see a particular number, then I would say no or say yes. But it's a bit more complicated to go through, so I won't touch that right now. So I hope that answers the question. Obviously, it's really, really important that we are able to communicate, not just to other customers, but also to internally why our model makes certain predictions. And I think, again, the fact that Alteryx has this inbuilt makes it a really, really good tool for that purpose.
And I'd like one last point I'll add to that is obviously for our customers, we wouldn't be going in detail and bombarding them with a lot of variables or ifs and buts and all that. So the simple way that we do is that we visualize and on a high level show them that, model A, here are the results, and model B, here are the results, and here is something that you need to understand. And some of you have been asking about where to learn more about Alteryx. Alteryx community and Alteryx Academy, fantastic places for you to start or get better. They do lunch and learn videos every week. They have interactive training lessons on the community. So be sure to check out both these platforms. The Academy is a part of the Alteryx community, so you can find everything on there. So thanks everyone for joining. We'll just stick around for 5 more minutes. Do you have any questions? Feel free to post them in the Q&A section or the chat box. Happy 4th of July to everyone, and we hope that you have a fantastic long weekend.